Hello, everyone. Thank you for listening. We are Team 8, and we'll be presenting our collaborative project with Unilever centered on developing new skincare products by exploring different aeration techniques.
We were tasked with investigating different aeration techniques and to assess the scalability with each one. The goal for this project was to design a process that could be implemented at a large scale to aerate any lotion brand. This is important because designing a successful aeration method would allow Unilever to maintain a competitive advantage over other beauty care companies.
So before creating our design, it was key to understand the technical background of the project. The concept of aeration is the dispersion of the gas phase into a continuous phase or medium. The primary goal for aerating our product is to maximize the number of bubbles present in our formulation whilst reducing the bubble size distribution, as this contributes to improving the product's sensory and stability. However, the challenge with aerating is that there will be a variability of bubble size distribution for each lotion brand that we tested. Hence, it was then important that for a proposed technical solution that it accounts for this and is adjustable to a wide range of skincare products. The main question is then, from a fundamental standpoint, how can we predict the bubble breakage and formation once we inject our gas? Through average research, we concluded that we hypothesized that it will occur once the capillary number Ca of our specific lotion brand exceeds a critical stress. This theory was then critical to our design because, as we can see from the plot on the right, if our capillary number as a function of the viscosity ratio is altered by changing the flow conditions, it will end up at the top of the curve, and we can theoretically then predict bubble breakage will occur for a product. As such, by evaluating question 1, it was then key that a tunable variable for aerating our product will be the shear rate, which from a pilot plant scale viewpoint, we expect will primarily occur within the mixing tank or along the pipe flow, which can all be theoretically estimated with known equations. Lastly, as we mentioned, we are concerned with creating stable products before it reaches the hands of our consumers. So to create a stable product, we first had to understand what factors control our product stability, and that was shown to be the bubble coalescence and also ripening mechanisms, which we found could be controlled if we have a lower Laplance pressure in our aerated product.
The team was given 5 different lotions from various Unilever brands in order to aerate at a bench scale and evaluate their effectiveness. The first challenge was finding a way to inject nitrogen gas into each of the lotion brands, which is essential for introducing bubbles into the product. In order to achieve this, we ordered a nitrogen charger online and attached the top of it to a small beaker containing lotion from a particular brand. Directly after injection, we utilized an overhead homogenizer to shear the aerated lotion sample at various speeds, which is essential for reducing the overall bubble size distribution within the product. We homogenized each lotion sample at 5,000 and 9,000 RPM in order to observe how the rheology differs at low and high speeds. Next, we put the aerated sample through an ARG2 rheometer, which has a built-in software that creates rheology profiles for the user at desired conditions. The rheology of the aerated samples were compared to the initial sample in order to observe how the viscosity and shear stress changed as we apply shear. Lastly, we performed image analysis of the initial and aerated lotion samples in order to verify that bubbles formed within the lotion and that bubble breakage occurred after homogenization. This process was repeated at the exact same conditions for each of the 5 brands. Due to company confidentiality, the team could not discuss which specific products and brands we performed our experiments on, so the experimental results above we will refer to as Lotion A. As previously stated, having a low viscosity is key for the desired sensory we are trying to achieve. Following aeration and homogenization at 5,000 and 9,000 RPM, we used the rheometer to develop a rheology profile, which essentially plots the viscosity versus shear rate of the lotion. We then take the log of both sides in order to linearize the plot, which can be seen in Figure 1. We can see a clear decrease in viscosity versus shear rate for Lotion A aerated at both RPM ranges. Figure 2, on the other hand, displays the shear stress versus shear rate of Lotion A and shows a clear decrease for the aerated samples as well. Overall, the data shows promising results in the viscosity and shear stress both significantly decreased after the implemented aeration process. The team relied on image analysis to verify bubble formation after aeration, as well as bubble breakage after homogenization. Figure 3 showed the initial sample of Lotion A before aeration, and there are essentially no bubbles. Figure 4 showed Lotion A after nitrogen injection, and from this image we can see clear bubble formation throughout the sample. Using a microscope scale, we measured the largest bubble in the aerated sample to be 150 microns. Figure 5 shows Lotion A after being aerated and homogenized at 5,000 RPM, and there's clearly a small bubble size distribution occurring within this sample. The bubble size decreased as well as we measured the largest bubble to be about 50 microns, a significant decrease from the aerated sample. As desired from Unilever, our proposed technique was successful in increasing the number of bubbles while also reducing the bubble size distribution throughout the product.
We were able to successfully aerate each of the lotions that Unilever sent us, but depending on the properties of each brand, we noticed that there was difficulty in bubble trapping. The lotions we had to aerate were different in viscosities and emulsion type. Out of the two, oil and water emulsion showed more promising results after aeration and homogenization. We were able to see bubbles forming after aerating lotion A, and once we homogenized the samples, we concluded the bubbles got smaller after conducting image analysis after both aeration and aeration plus homogenization. 5,000 RPM lowered the viscosity for lotion A, creating a sweet spot where it was good for bubble breakage, but didn't consume as much energy from higher shear rates. After we aerated lotions, we applied it to our skin to see if there were any differences in the way the lotion felt. We applied the lotion to both hands at the same time, and after aerating and homogenizing, the lotion felt slightly smoother when being applied to skin.
So from a bigger standpoint, we hope that implementation of our technical solution will advance Unilever's outlook in the skincare developing and emerging market, and hopefully will attract new customers due to the desired whip feel appearance of our newly designed products.